This is the third lecture of the third week, and today we're going to cover the omitted variable bias. So we said in the previous lecture that the error term arises because there are factors that are not included in the model but still affects our dependent variable. So for simple linear regression, we have an intercept and one independent variable. And then there are other terms that could potentially impact our dependent variable y, but it's not included in the model as a regressor. So whatever is not included in the model as a regressor is all included in this error term u. The problem is that sometimes omitting some of these variables can lead to OLS bias, or beta 1 being biased. So in order for us to say that there's an omitted variable bias, there has to be two conditions that are met. First, the z, the omitted variable, is a determinant of y. And second, z is correlated with the regressor x. So let's go back to our policy problem of trying to determine what impacts the test score. So in this model, we had a test score as a dependent variable and a student-to-teacher ratio as an independent variable. In this case, we can say that perhaps the percentage of English learners in the district is an omitted variable. This percentage of English learner can directly impact the test score because the larger percentage of students are trying to learn English, then maybe the test score can be actually lower. So the first condition is met. Z, which is a percent English learner, is a determinant of Y. Also, if there's a high percentage of English learner, it could mean that there's also high students to teacher ratio because immigrant communities with the higher percentage of English learner can be poorer, meaning that they also have lower school budget and higher students to teacher ratio. So the omitted variable and the regressor that's already included in the model are correlated. So since two conditions for the omitted variable bias are satisfied, we can say that in this case, there is an omitted variable bias and hence the beta hat 1. When we estimate beta 1, then this would be biased. Let's talk about two other examples. So first example is the time of the day when students take tests. So in this case, where we have test score as a dependent variable and student-to-teacher ratio as an independent variable, when students actually take the test, whether it's morning or afternoon or evening, could potentially impact the test score. So the first condition is met. But then when students take the test, it's probably not related to how many students there are per teacher. So the omitted variable of the time of the day of the test and the student-teacher ratio are not correlated. So the second condition is not met, and so we don't have an omitted variable bias in this case. The second example is the number of parking lots per pupil. So in this case, the number of parking spaces is probably correlated with how many students there are per teacher, because we can assume that the more parking space there is, there's also more students per teacher. But then the problem is that the number of parking spots don't directly impact the test scores. So in this case, the first condition is not met, the second condition is met, so there is no omitted variable bias. So we said that omitted variable bias leads to OLS estimator being biased. So let's talk about the biasness of beta hat 1. So here's a formula for how, when there's omitted variable bias, how much bias there is. And when there is no omitted variable bias, beta hat 1 should converge to beta 1 as the sample size becomes larger. But in the case when there's omitted variable bias, beta hat 1 doesn't converge to beta 1. It converges to beta 1 plus some term over here. So what does this mean? We said that omitted variable bias occurs when omitted variable z is a determinant of y and omitted variable z is correlated with x. So if omitted variable z is correlated with x, that means that the correlation with x and z, correlation between x and z is not equal to 0 because they're correlated. But if correlation between x and z is not equal to 0, that means that correlation between x and u is not equal to 0 because z is part of u. The omitted variable is included in the error term. So basically, the correlation between x and u is not equal to 0. And we also denote this correlation between x and u as rho of x and u. So what does this mean? Even when there's a large sample size, beta hat 1 would always be biased when there's omitted variable bias. And that's because even with the large sample size, if there's a correlation between x and u are not equal to 0, then this term is positive. So beta hat 1 converges to something that is beta 1 plus some number. So it never converges to true beta 1, but beta 1 plus some term. So beta hat 1 is always going to be biased. The second thing is that the absolute value of correlation between x and u determines how large the bias is. So if the rho of x and u is large, then this entire bias becomes large. And beta hat 1, the bias for beta hat 1 would actually increase. So it will be really far away from the true beta 1 that we want to measure. The last thing is that the direction of the bias is determined by the relationship or the correlation between x and u. So if x and u are positively correlated, then this means that this term is positive. This entire term is positive. So beta hat 1 would converge to something that is beta 1 plus some number. So it would always overestimate the true beta 1. And the other way around, if the correlation between x and u are negative. So if that's the case, this entire term would become negative, which means that now beta hat 1 will converge to something that is less than true beta 1. So beta hat 1 would always underestimate beta 1. Let's go back to our omitted variable bias case, where we're omitting the percentage of English learners in the district from the model. So in this case, when you have a lower percentage of English learners in the district, it's likely that the test scores will be higher and the student-to-teacher ratio is likely to be lower. And because the omitted variable, which in this case is a percentage of English learner, and the student-to-teacher ratio are positively correlated, and they're positively correlated because they are moving in the same direction. When you estimate the model without including this omitted variable, your estimate of beta hat 1 would be biased, and they're biased in positive way, meaning that it would be overestimated. And that's because when you omit one of the variable, the percentage of English learner in this case, the student-teacher ratio actually overestimates its true effect because it's not accounting for the effect of percentage of English learners. And also because we said in previous slide that if the correlation between x and u are positive, then the true beta is overestimated when you're estimating beta hat 1. So what can we do when there's an omitted variable bias? One way is to hold the omitted variable constant. In this case, we can fix the percentage of English learner constant. So first thing to note from this table where we look at the test score difference between small and large class by percentage of English learner is that the smaller the percentage of English learner, the higher the test score. And the larger the percentage of English learner, the lower the test score, meaning that there is a negative relationship between the percentage of English learner and test scores. Another thing to note is that in general, when the class size is small or the student-teacher ratio is less than 20, the test score tends to be higher than test score of the larger class. Lastly, when we were looking at the difference between test score between small and large class size, without controlling for the percentage of English learner, we said that the test score difference was 7.4. But when you look at the test score difference, holding the percentage of English learner constant, then the test score difference becomes much smaller than 7.4. So for instance, when we look at the percentage of English learner between 8.8 to 23% and look at the test score difference, then it's only 5.2, which is less than 7.4. This shows that when you don't control for the percentage of English learner and you have an omitted variable bias, the estimate of the effect of class size is much overestimated than the true effect. So in the next lecture, we'll discuss another way of dealing with an omitted variable bias. And it'll be called multiple linear regression, where we include the omitted variable in the regression model.